Okay, we're going to talk about synthetic routes and stereochemistry in this topic, and synthetic routes is going to sort of put together everything we've learned, and stereochemistry we're going to look at some new information. Okay, so when we talk about synthetic routes, what we're really doing is we're figuring out how to get from one substance to another substance. So we're putting together multiple different reaction types to figure out how to get from point A to point B. So you might remember on practice worksheet 10-2, you had that diagram right at the beginning that showed how all the things were connected. That might help you as you get started with these. I would encourage you not to use that as a crutch, but if you're really, really stumped on a problem on the homework, you might use that just to help you get going. Okay, so let's look at an example. Deduce a synthetic route for the synthesis of ethanal from ethene. Okay, so we're starting with ethene, and we're trying to get to ethanal. So some people find it helpful to work backwards, and some people find it helpful to go forwards. I think it's a little easier to work backwards. All right, so ethanal. What did we most likely form that from? So if I see an aldehyde, I'm immediately thinking that it's a product of oxidation. So I'd go back one step and say, okay, I must have had ethanol here. And anytime you're doing a reaction like this, you should always state the conditions. So this is an oxidation reaction. So I'll just label it as such. You don't necessarily need to label it unless it asks you to describe the type of reaction, but just for your notes. So you would need either potassium permanganate or potassium dichromate. You could say either one. Acid conditions and a little bit of heat. And because we're trying to make the aldehyde and not continue the carboxylic acid, we're going to just distill this as it forms. Okay, if we wanted to produce the carboxylic acid, we need to continually react it under reflux. Okay, so then I have to ask myself, how could I get from ethene to ethanol? Okay, so in order to do that, basically I'm going from an alkene to a substituted alkane. So that must be an addition reaction. So this is addition. So I'm adding water here in the presence of acid, and that will give me ethanol. Okay, so I want you to try the next two. They're on your guided notes, but take a minute and see if you can figure out how to get from 1-bromobutane to butanoic acid. Okay, so to get from 1-bromobutane to butanoic acid, I'm going to start by drawing the structures. And you don't necessarily have to draw the structures unless it says to. If it just says to state an equation, you could just write the formula. But there shouldn't be any problem if you draw the structures. And for me, I think it's easier if I'm trying to figure out what's going on to draw the structures. It just helps me. All right, and I'm not going to draw the hydrogens because, again, I'm going to try to keep this as simple as possible. So I'm starting with 1-bromobutane, and I'm trying to get to butanoic acid. Okay, so again, if I'm not sure where to go, I could go from either end here. Okay, so when I see a halogenoalkane like this, I'm going to say, okay, well, I know these react via nucleophilic substitution, so that's a possibility. And then when I look at butanoic acid, I'm going to say, okay, that tells me it's quite possibly a product of oxidation. All right, so let's work backwards from here. All right, now, I can make this from butan 1-ol. And in order to get the carboxylic acid product as opposed to the aldehyde, I would need to react it under reflux. So I'll use the other reagent here, potassium dichromate, but you can use either one as an oxidizing agent. And here we'd need to react under reflux. Okay, so how can I get from 1-bromobutane to butan 1-ol? I can use nucleophilic substitution. And so I'm going to need a source of hydroxide. Sodium hydroxide would work just fine, so I'm going to add the hydroxide in this step. And because this is a primary halogenoalkane, this is going to react via SN2. So for SN2, I have to think also about what kind of solvent I should use. So you should use some kind of aprotic solvent, like propanone. Now, I doubt you need to state the solvent type unless you're specifically asked, but it doesn't hurt to have that information ready to go. Okay, so we got from point A to point B in 2 steps. All right, now let's look at another one. Okay, so this is going to be 3 steps. So deduce a synthetic route for the production of propyl ethanoate from ethene, and we're going to need one other reactant in the last step. Okay, so propyl ethanoate is an ester. So right away I would say, okay, I know an ester forms from a condensation reaction. So in my last step, I must have reacted, I'm starting with ethene. So that must lead to the ethanoate part. So in my last step, I must be reacting ethanoic acid with propan-1-ol. So somehow along the way I formed ethanoic acid and I reacted it with propan-1-ol. And that's how I got propyl ethanoate. And the conditions for this last step would be you need sulfuric acid, you need gentle heat, and this is a condensation reaction. Okay? Now I started with ethene. And somehow I got from ethene to ethanoic acid. All right, so this is going to be really similar to the last one in that we're going to have an oxidation step. So the step that leads to ethanoic acid is an oxidation. And again, that's an oxidation under reflux because we're getting to the carboxylic acid. Okay, and for this we need an oxidizing agent. This time I'll use potassium permanganate, acid, and a little bit of heat. And then to get from ethene to ethanol, I can do an addition reaction. And I need acidic conditions for that to occur. Okay, so it really generally is helpful to work from backwards, going back to the beginning. Okay, and this is an addition reaction. This is one of those things that as you study reaction types, you're going to get better and better at because it's really just understanding how it all comes together. So doing these problems is a great way to test if you really know the material or not, because if you can come up with these synthetic routes, you really do know your reactions quite well. Okay, so let's talk about stereoisomers, and this may be a hard one to do via video lesson, but I'm sure going to try. And in class, we'll look at some models and stuff like that that I think will help you understand it a little bit better. Okay, so a stereoisomer. Stereoisomers are isomers that have identical molecular formulas and bond multiplicity, but they are arranged different spatially. So you'll see multiple different examples of this that'll make that make a bit more sense. But when we look at the isomers, we've already talked about structural isomers like butan-1-ol and butan-2-ol. Stereoisomers have a lot more to do with the arrangement of atoms in space. They're not just connected differently. So we have 2 main types of stereoisomers, conformational isomers and configurational isomers. So conformational isomers are really rapidly interconverting, and you don't have to break any bonds to go from one isomer to the other. Configurational isomers, on the other hand, can only be interconverted by breaking a bond or by rearranging atoms. Okay, so conformational isomers, you're going to have both occurring rapidly. Configurational are going to be a little harder to change from one to the other. Okay, so let's talk about conformational isomers first. So these occur via rotation around a single sigma bond. Now, you might remember from our bonding unit that when a sigma bond is formed, it has axial overlap. So because the overlap is on the bond axis, it can rotate freely, okay? So the 3D arrangements of these can rapidly interconvert. You really can't isolate or separate an individual conformational isomer. It's just not possible, okay? So again, when we talk about if this is the bond axis, a sigma bond would be formed by orbital overlap like that, okay? So it can rotate freely around that bond axis. And these are going to differ from each other based on the arrangements of atoms around that single bond. So let's look at some examples to show what we mean by that. Okay, so for ethane, we have something called Newman projections. We have them for other molecules as well, but it's really easy to see with ethane. So if this is ethane, and that's not the greatest drawing you've ever seen in your life, but that's okay. When we look at a Newman projection, it's like we're looking down this bond from one carbon to the other. Okay, so you'll see something that looks like this. So this dot right here, that's like the bond axis, and I'm looking straight down it. Okay, so these are the hydrogens on one of the carbons. And there's two conformations, staggered and eclipsed. So this is the staggered conformation. And this is a little more stable. There's less repulsion because they're very evenly spread apart. And then this is the eclipsed conformation. So as you can see, there's really nothing preventing ethane from rapidly going between those two conformations, staggered and eclipsed. Okay. And in cyclic hydrocarbons, we have, well, this is a good example with hexane, but they have multiple, the rings can basically move a little bit. So hexane is the most common example that you see, and we have boat conformation and chair conformation. So it's sort of like they're just flipping back and forth. And you don't necessarily need to know boat and chair, but this is just an example of a conformational isomer in a cyclic hydrocarbon, where they're just kind of flip-flopping back and forth. Okay? Now, configurational isomers cannot freely and rapidly interconvert, and there's two possible reasons. Okay? The first is lack of rotation around a double bond. So when we think about how orbitals overlap, if this is my bond axis, the sigma bonds form by direct overlap. But a pi bond is above and below, right? So the overlap is happening here and here. So that kind of locks it in place and doesn't allow free rotation, okay? And then the other reason that they can't rapidly interconvert, we'll have to look at specific examples to understand that, is that in order to change between the isomers, we would have to break a single bond. So we'll talk about that. So the first reason pertains to cis, trans, and EZ isomers, typically, and the second pertains to optical isomers. Oops, sorry. All right, so cis and trans isomers. Let's talk about those. So cis and trans isomers are determined by the position of substituents, so things attached to carbons, that are relative to a reference plane. So that reference plane is either going to be a double bond in alkenes, or it's going to be a ring in cycloalkanes. So if it's a cis isomer, that means the substituents are on the same side of the reference plane, and trans means they're on opposite sides of the reference plane. All right, so let's look at some examples. A cis isomer might look like this. So this is but2-ene, and in the cis, so this is cis but2-ene, and in the cis isomer, both of the methyl groups are on the same side of the reference plane, which is the double bond. So in the trans isomer, those methyl groups would be on opposite sides of the reference plane. So this is trans but2-ene. Sorry, that dash is a little hard to see. Okay. Now you can also see this with cycloalkanes. So I'll draw this up here maybe just to give more space. So this is cyclobutane. And these wedges, again, just mean that it's sort of coming forward. So this is a plane. And in cis 1,2-dimethylbutane, oops, sorry, both of the methyl groups are pointing down from the reference plane. So imagine that these are coming forward, so it's sort of flat in, it's sort of perpendicular in relation to the board, if that makes sense, or parallel to the floor. And then in the trans isomer, it would look like this. And again, my artwork leaves something to be desired. I am sorry. So the one methyl group is pointing upwards relative to the reference plane, and the other is pointing downwards. So this is the cis isomer, this is the trans isomer, and it's trans 1,2-dimethyl cyclobutane. And this would be cis 1,2-dimethyl cyclobutane. So these exist because there's restricted rotation either around the double bond or around a ring. You can't just have things flipping around in either of those cases. Now the cis isomer is usually polar and the trans isomer often isn't because the dipole moments will often cancel out on either side. So typically, as far as boiling points go, we'd expect them to be a little higher in the cis isomer, and we'd expect the reactivity to also be a little bit greater in the cis isomer because we're likely to have things like partial charge that could attract a nucleophile or something like that. So there are some different properties between cis and trans isomers. We don't expect them to be identical. Now, sometimes the designation of cis or trans isomer is insufficient. So let's look at an example where it would be insufficient. Now, in this molecule, I have 4 different groups around the double bond. So I really can't say, like if I say cis, which 2 groups am I talking about that are on the same side of the double bond? Okay? So I'm going to use the system called the EZ system, and we're going to use priority. So we're going to prioritize all 4 of these substituents. We're going to rank them according to atomic number. So for the most common substituents we'd see, iodine would have the highest priority because that is the largest atomic number, and hydrogen would be the lowest. So I'm going to look at my molecule here and I'm going to rank these. So this is my first priority, second, third, and fourth. If both of the highest priority substituents are on the same side of the double bond, we would say that that's the Z isomer. If they're on opposite sides of the double bond, it's designated E. Okay, so Z is sort of like cis and E is sort of like trans. Okay? So this is a Z isomer because they're on the same side of the double bond. Okay? This is a mess to name, but I suppose we could. This is Z, alphabetizing. 1 bromo, 1 chloro, 2 iodo ethene. What a mess. And I made this carbon 1 because I wanted to give the overall lowest numbered substituents. Okay, so let's look at an example. Okay, so, and it'll really help, just like we did in the last topic, it'll really help to condense all the chain that is not related to the double bond. So I'm condensing the rest of this chain because I'm really focusing in on the double bond here. Okay, so let's prioritize all these substituents. Iodine would be the first priority, bromine would be the second priority, the ethyl group would be the third priority because we're looking at carbon here, and hydrogen would be fourth priority. Okay, so that means the high priority groups are on the same side of the double bond. So this would be Z, and we usually put in little brackets here. 1 bromo, 2 iodo, but 1 ene. Okay, and we could draw the trans isomer of that. or sorry, the E isomer. So this would be E, and then the rest of the name would stay the same. Okay? This takes a little getting used to and a good amount of practice. But again, just keep working at it and you'll get it. And prioritizing them is not so hard once you know what you're doing. Okay, last part of this is chirality and optical activity. And this is an interesting topic. So you've probably never heard the word chiral before, but a chiral carbon is any carbon that's attached to 4 different atoms or group of atoms. So any molecule that contains any one chiral carbon can be described overall as chiral. When chirality exists, there are 2 ways to arrange groups around the chiral carbon. And these form non-superimposable mirror images called enantiomers. So here's an example of what we mean by that. So this right here is like the mirror plane. So you can see these are mirror images, but they're not superimposable, and here's why. If I draw around in a circle along the base of the tetrahedral, it goes around in this direction. It goes hydroxyl, methyl, and hydrogen. If I start at the hydroxyl and do the same thing around the base here, it's hydroxyl, hydrogen, methyl. So these are not superimposable, okay? It's easier to see with an actual 3D model, and so we'll look at those in class because it's just much easier to see what we mean by that, okay? So these are enantiomers, and again, non-superimposable mirror images. When you're trying to draw these, I would draw the mirror plane and then try to exactly replicate it on the other side. Now, when we look at the properties of enantiomers, there is very little difference in physical or chemical properties that's easily observable. The one major easily observable difference is that the 2 enantiomers will rotate plane polarized light differently. So one will rotate it clockwise and the other will rotate it counterclockwise. This is why these are called optical isomers, because this is optical activity. So any molecule with a chiral carbon is considered to be optically active, and we can use a polarimeter to detect this. Now, enantiomers, although in a lab it would be really hard for us to tell the difference between them, they do differ in their reactions with other optical isomers. So a lot of times this is in biological systems. So a good example of this is limonene. There are 2 optical isomers of limonene. One is found in lemons and oranges, and it has that citrusy kind of smell. The other is found in pine needles and has very different, they're very distinguishable. They're not similar at all, really. And another example of enantiomers that are different in biological systems is thalidomide. And so you may or may not have heard of this before, but back many years ago, they discovered this drug, thalidomide, that was really effective at curing morning sickness in pregnant women. And so it was pretty widely used. And unfortunately, they found that while it was very effective at curing morning sickness, there were 2 enantiomers of this drug. And the second enantiomer caused terrible birth defects. So obviously, they don't use that for morning sickness anymore because it's very hard to just have one enantiomer. So that was a really tragic occurrence. They've actually found that that drug is good for other things, so it can be used to cure leprosy, oddly enough. And so they will use it in men or in women that they know are not pregnant, but they can't use it for its original intended purpose anymore. Okay, so the body can differentiate between 2 enantiomers. Now, when we use the term racemic mixture, that's a 50-50 mixture of the 2 enantiomers. So if you have a racemic mixture, if you're looking at them with a polarimeter, they kind of cancel each other out. So that mixture will not be optically active. And usually this is produced in lab settings. So if I'm synthesizing a compound that has enantiomers, I'm going to make a 50-50 mixture of them. There are ways to just make one, but it's quite tricky, and we'll talk about that in the medicinal chemistry unit, actually. We can do something using chiral auxiliaries, but it's not typically what happens. But in nature, when we're using enzyme-catalyzed biochemical reactions, they produce just one enantiomer, and so therefore those are optically active. So turpentine is both naturally occurring and can be synthesized. And so you can tell the difference between synthetic and natural turpentine, because synthetic turpentine will not be optically active because it's a racemic mixture, but natural turpentine does show optical activity because it just produces one enantiomer. This is a lot to think about and process. I really recommend that you check out the section in the textbook on this. It has some good diagrams too that will help you understand this, and we'll also look at models in class.